Greetings, mathophiles, and welcome to the first in a series of 3 videos on binomial probability. This first one will involve an introduction and will lead up to the formula. The second one will involve how to use the commands on the TA84 calculator that are related to binomial distributions. And the third one will take a look at location and spread for various binomial distributions and sort of how that all works. I will place links in the description to each of the other 2 videos in this series, so you can check for those. You're going to get the most out of these videos if you know something already about combinations and about independent events. I have a video on independence, and I'll place a link to that in the description as well. We're going to begin by looking at Brianna, who is a basketball player who makes 65% of her free throws. Suppose she takes 5 free throws in a game and that the shots are independent. The first thing we're asked to do is to list the 32 outcomes in the sample space. And by outcomes, we mean strings of misses and hits. So for example, if she hits all her shots, that's an outcome. If she hits the first 2 and misses the last 3, that's an outcome, and so on. There are 32 of these because there are 2 possible outcomes for each of the free throws, and we have 5 of these in a row. So 2 times 2 times 2 times 2 times 2 is 32. Now, you're going to need some sort of organized way to do this, right? Because there's a lot to keep track of. You don't want to miss any. You don't want to repeat any. And so we could start by imagining that she hits them all. And then we could imagine that she misses one. The one that she misses could be the first, or it could be the second, and so on. And I will not bore you with the creation of this entire list. We're just going to reveal the 32 outcomes. So H stands for hit, M stands for miss, and these are they. Here's a hint on how to organize these if you ever have the fortune to have someone require of you that you do that. We know that there are 32 outcomes because that's 2 to the 5th. And we know that of those 32, half, or 16, have to begin with her making the first shot, and half have to begin with her missing the first shot. So I would start out with just a single column of 16 hits and 16 misses. And then of the 16 outcomes that begin with a hit, half, or 8, have to continue with a hit, and half have to continue with a miss. So I would then make the second column with 8 hits and 8 misses following the hit on the first shot. And then I would do the same thing for the half of the outcomes that involve a miss on the first shot. And I would just keep cutting those in half. So I'd alternate by 4, and then by 2, and then finally by 1, and then I would have my, my list of outcomes as you see here. Second problem, what, dear me, what is the probability that she misses the first 2 shots and hits the last 3? Well, if these are independent events, if the outcome of one shot doesn't influence the outcome of any of the other shots, then I can multiply the probabilities. And so if she misses a shot, if she makes them with 65%, she misses them with 35% likelihood, right? So she misses the first shot with probability 0.35. She misses the second shot with probability 0.35. And she makes each of the last 3 with probability 0.65. So if I take the product of these 5 numbers, that should give me the probability that she misses the first 2 and hits the last 3. And I will tell you that that is about 0.034. Now, this should be the probability of any outcome that involves her missing 2 and hitting 3, right? So it could be that she hits the first 3 and misses the last 2. It could be that she starts with a hit and then alternates thereafter. It should be the case that any of these outcomes that involve 2 misses and 3 hits also has a probability of 0.034, right? It shouldn't matter what the ordering is of the misses and hits. What should matter is that there are 2 misses and 3 hits. And I multiply the same set of 5 numbers in any of those cases. So that's sort of a lead into the third question here, which is what's the probability that she hits any three of the five shots? In order to answer that, we need to know two things, one of which we have already, and that's the probability of any one of these outcomes. The second thing we have to know is the number of outcomes out of the 32 that involve having two misses and three hits. One thing you can do is you can simply go through this list and count up one by one all of the outcomes that involve two misses and three hits and hope that you don't miscount. I will tell you for free that if you do that, you're going to find that there are 10. But there is, in fact, an easier way to figure out that there are 10, and that is to recognize that we have 5 attempts. And out of those 5 attempts, 3 are going to be made. So we can ask ourselves, what's the number of combinations of 5 things taken 3 at a time? And choose r, as you may know, is n factorial over r factorial times n minus r factorial. So 5 choose 3 is 5 factorial over 3 factorial times 2 factorial, and a little bit of finagling reveals that that's 10. And so if she's to make any 3 of the 5 shots, there are 10 ways that that can happen. Each of those outcomes has a probability of 0.034. So the probability that she hits any 3 ought to be 10 times 0.034, which is about 34%, 0.34. Let's see whether we can generalize this result and find ourselves some sort of a formula. So suppose she hits free throws with probability P, and suppose she takes N free throws in a game and that the shots are independent. What's the probability that she hits K of her N shots? Well, first let's figure out the probability of any one of the outcomes that would involve making K of the N shots. So she makes shots with probability P, and she misses them with probability 1 minus P. And in this situation, we're imagining she's going to make K of those shots, which means she's going to miss the rest. And if you take N shots and you make K of them, how many are you going to miss? You're going to miss N minus K. So this should be the probability of any of the outcomes that involve making K shots with probability P, missing N minus K shots with probability 1 minus P. Now, how many such outcomes are there? Well, it should be N choose K, right? The number of ways I can get K of the N shots to be hits. So there are a couple of notations for that. I like this one. N choose K, or number of combinations of N things taken K at a time. This is the probability of K successes in N of these trials with probability P of success on any individual trial. This is called a binomial probability because it satisfies a number of conditions. What do we have to assume? Or what are the conditions that we have to have in play before we can use this formula? Number 1, we have to have a fixed number of trials. Right, so it's not one of these situations where we maybe keep going until a certain thing happens or keep going until something happens a given number of times. We're deciding ahead of time there's going to be a fixed number of trials. In our first numerical example, it was 5 shots. Here we generalized it to N shots. Second, each of those trials has an either-or outcome. One of two things is going to happen. So it could be that a shot is made or missed. It could be that a coin comes up heads or tails. It could be that a patient in a clinical trial is cured or not cured. Any kind of situation where you have an either-or result. Some results that are not inherently either-or can be reframed so that they are. For example, if you roll a die, 6 things can happen. But if you choose to interpret the outcome of a die roll as odd versus even, or 5 versus all the other numbers, you can sometimes apply a binomial probability in those cases as well, as long as the thing that you're focusing on is an aspect of this situation that comes out either one way or another. Third thing we're assuming is that the same probability applies to all the trials. So it's not going to be, 65% for the first half of the game and, 69% for the second half of the game or something like that. It's going to be the same probability all the time. And finally, in order to allow us to multiply these probabilities, it had to be the case that the trials are independent. So there's nothing about making or missing the third shot that's going to have any effect on whether she makes or misses the fourth shot or any other subsequent shot. So that is a quick introduction to binomial probabilities with the conditions and the formula. Any situation that involves these four assumptions or these four conditions can be thought of as binomial in terms of the probabilities, and you can use this formula here. In the following two videos, we will address calculator commands and the shapes of distributions and their locations. Happy mathing.